The typical output current total harmonic distortion, or THD, for UPS with a 100% nonlinear load typically ranges from 5 to 10%. This range is based on several considerations. Firstly, the International Electrotechnical Commission, or IEC, Standard 62040.3 specifies a maximum output current THD of 8% for UPS systems used in power distribution systems. Secondly, the Institute of Electrical and Electronics Engineers, or IEE, Standard 1100, also known as the Emerald Book, recommends a THD of less than 5% for nonlinear loads. Thirdly, practical experience in the field typically shows THD values between 5 and 10% for UPS systems supplying nonlinear loads such as servers, computers, and power supplies. The output current THD of a UPS is influenced by several factors. Firstly, rectifier efficiency affects the input current waveform, which can introduce harmonics into the UPS output. Secondly, inverter efficiency affects the output voltage waveform, which can also introduce harmonics into the output current. Thirdly, some UPS systems incorporate active harmonic compensation circuits to reduce the output current THD. Fourthly, nonlinear loads, such as electronic equipment, generate current harmonics that can be reflected back to the UPS output. The lower the output current THD, the better the UPS is at supplying power to nonlinear loads. If the output current THD is too high, it can cause problems with sensitive equipment or other devices connected to the UPS. A deeper dive into these factors can help understand how UPS handles nonlinear loads. The rectifier converts alternating current, or AC, to direct current, or DC, and its efficiency determines how cleanly it performs this conversion. A less efficient rectifier can introduce harmonics into the DC bus, which then propagates to the output. The inverter converts DC back to AC, and again, its efficiency impacts the cleanliness of the output waveform. Inverters with poor efficiency or inadequate filtering can generate voltage harmonics that in turn affect the current THD. Active harmonic compensation circuits actively counteract the harmonics produced by the load. These circuits typically use filters or active injection techniques to cancel out harmonic currents, resulting in a cleaner output waveform. Nonlinear loads draw current in short, discontinuous pulses rather than a smooth sinusoidal wave. This behavior generates harmonics. Examples of nonlinear loads include computers, servers, variable frequency drives, and LED lighting. Standards like IEC 62040.3 provide benchmarks for UPS performance under nonlinear load conditions. Adhering to these standards ensures that UPS systems maintain power quality within acceptable limits. IEE Standard 1100 offers guidance on mitigating harmonic distortion in electrical systems, including recommendations for UPS applications. Aiming for a THD of less than 5%, as suggested by IEE 1100, can improve the reliability and performance of sensitive electronic equipment. Monitoring THD levels in real-world installations can provide valuable insights into UPS performance and load characteristics. Field measurements often reveal variations in THD depending on the specific load mix and operating conditions. The relationship between input and output current THD is complex. While a UPS can filter input current harmonics to some extent, it cannot completely eliminate them. Harmonics present in the input current can still propagate through the UPS and affect the output current THD. The UPS internal design and filtering capabilities play a crucial role in minimizing the impact of input current harmonics on the output. The size and type of the UPS also influence its ability to handle nonlinear loads. Larger UPS systems typically have more robust filtering and harmonic compensation capabilities. Online double conversion UPS systems generally offer better harmonic performance compared to line interactive or standby UPS systems due to their continuous power conditioning. When selecting a UPS for nonlinear loads, it is essential to consider the load's harmonic characteristics. This involves analyzing the types of equipment connected to the UPS and their individual harmonic contributions. Oversizing the UPS can provide additional headroom to accommodate harmonic currents without exceeding the UPS rated capacity. Regular maintenance and monitoring of the UPS are crucial for maintaining optimal performance. This includes checking the UPS filters, capacitors, and other components for signs of degradation or failure. Monitoring THD levels and other power quality parameters can help identify potential problems early on. Understanding the interplay of these factors allows for informed decisions when specifying, installing, and maintaining UPS systems in environments with significant nonlinear loads. It also ensures the reliability and longevity of connected equipment. The efficiency of the rectifier and inverter sections within the UPS contribute significantly to its overall harmonic performance. High-efficiency designs minimize the introduction of harmonics during the power conversion process. Rectifiers that employ active power factor correction, or PFC technology, can reduce input current harmonics, leading to a cleaner input waveform. Inverters that utilize pulse width modulation, or PWM techniques, can generate output voltage waveforms with lower harmonic content. The UPS control system plays a vital role in managing harmonic distortion. Advanced control algorithms can actively compensate for harmonic currents and voltages, improving the overall power quality. Some UPS systems incorporate adaptive control strategies that adjust the harmonic compensation based on the load's characteristics. The type of filtering used in the UPS also affects its harmonic performance. Passive filters, such as inductors and capacitors, can attenuate specific harmonic frequencies. Active filters, which use electronic components to inject compensating currents, can provide more effective harmonic mitigation. Hybrid filters, which combine passive and active filtering techniques, offer a balance of performance and cost. The location of the UPS within the electrical system can influence its harmonic performance. Installing the UPS closer to the source of nonlinear loads can minimize the propagation of harmonic currents throughout the system. Proper grounding and bonding practices are essential for reducing harmonic distortion and ensuring the safety of the electrical system. The impact of harmonic distortion extends beyond the UPS itself. High THD levels can cause overheating of electrical equipment, reduce equipment lifespan, and interfere with the operation of sensitive electronic devices. Harmonic currents can also create voltage distortion, which can further exacerbate these problems. Mitigating harmonic distortion is therefore essential for maintaining a reliable and efficient electrical system. The choice of UPS technology depends on the specific requirements of the application. Online double conversion UPS systems offer the highest level of power quality and harmonic performance, but they are also the most expensive. Line interactive UPS systems provide a balance of performance and cost, but they may not be suitable for applications with highly sensitive equipment. Standby UPS systems are the least expensive, but they offer the lowest level of power quality and harmonic performance. When evaluating UPS systems, it is important to consider their THD specifications. However, it is also important to look beyond the THD number and consider the UPS overall design and features. A UPS with a low THD specification may not perform well in real-world applications if it lacks adequate filtering or harmonic compensation capabilities. It is also important to consider the UPS ability to handle transient loads and voltage fluctuations. These factors can also affect the power quality and reliability of the system. Regular power quality audits can help identify potential harmonic problems and ensure that the UPS is operating within its specifications. Power quality analyzers can measure THD levels, voltage distortion, and other power quality parameters. The data collected from these audits can be used to optimize the UPS settings and identify potential upgrade or replacement. The installation and maintenance of UPS systems should be performed by qualified personnel. Proper installation practices are essential for ensuring the safety and reliability of the system. Regular maintenance, including battery testing and filter replacement, can help extend the UPS lifespan and maintain its performance. Staying informed about the latest UPS technologies and standards is crucial for making informed decisions about power quality management. Industry organizations such as IEE and IEC provide valuable resources and guidance on harmonic mitigation and UPS applications. Participating in industry conferences and training programs can help engineers and technicians stay up to date on the latest development. In conclusion, understanding the factors that influence output current THD in UPS systems is essential for ensuring reliable power quality in environments with nonlinear loads. By considering rectifier and inverter efficiency, harmonic compensation, load types, and industry standards, users can select and maintain UPS systems that meet their specific needs. Continuous monitoring and proactive maintenance are key to mitigating harmonic distortion and maintaining a healthy electrical system. Also, in addition to active harmonic compensation, passive filtering techniques can be employed within a UPS system to further reduce THD. These passive filters, typically consisting of inductors and capacitors, are tuned to specific harmonic frequencies and act as shunt paths, diverting the harmonic currents away from the load. While active filters provide more dynamic and precise harmonic cancellation, passive filters offer a cost-effective solution for mitigating specific harmonic frequencies. Hybrid filtering approaches, combining both active and passive elements, can provide an optimal balance of performance and cost. When assessing the suitability of a UPS for nonlinear loads, it is crucial to consider short-circuit current capability. Nonlinear loads often draw high peak currents during switching events, and the UPS must be able to supply these currents without experiencing voltage sags or instability. A UPS with a higher short-circuit current rating can better handle these transient demands. The UPS overload capacity is another important consideration. Overload capacity refers to the amount of current the UPS can supply for a short period beyond its rated capacity. Nonlinear loads can draw sustained overload currents, and the UPS must be able to withstand these overloads without tripping or shutting down. A UPS with a higher overload capacity can provide greater resilience in demanding applications. The type of batteries used in the UPS can also affect its performance with nonlinear loads. Valve-regulated lead-acid, or VRLA, batteries are the most common type of batteries used in UPS systems. However, lithium-ion batteries are becoming increasingly popular due to their higher energy density, longer lifespan, and better performance at high temperatures. Lithium-ion batteries can also handle high charge and discharge currents, making them well suited for applications with demanding nonlinear loads. The cooling system of the UPS plays a crucial role in its reliability and longevity. UPS systems generate heat during operation, and the cooling system must be able to dissipate this heat effectively. Overheating can lead to premature component failure and reduce UPS lifespan. UPS systems typically use forced air cooling, but some systems may also incorporate liquid cooling for improved heat dissipation. The altitude at which the UPS is installed can also affect its cooling performance. At higher altitudes, the air is thinner, and the cooling system must work harder to dissipate heat. UPS manufacturers typically provide altitude dating factors that specify the reduction in UPS capacity at higher altitudes. The communication capabilities of the UPS are also important for monitoring and managing its performance. UPS systems typically have communication ports that allow them to be connected to a network or a computer. This allows users to monitor the UPS status, battery voltage, load level, and other parameters. The UPS can also send alerts and notifications in the event of a power outage, overload, or other abnormal condition. Remote monitoring and management capabilities are especially important for UPS systems that are installed in remote or unattended locations. The UPS warranty is an important consideration when evaluating different models. A longer warranty provides greater peace of mind and protection against potential failures. It is important to read the warranty terms and conditions carefully to understand what is covered and what is not. Some warranties may exclude certain components or types of failures. The reputation and experience of the UPS manufacturer are also important factors to consider. A manufacturer with a proven track record of producing reliable and high-performance UPS systems is more likely to provide a quality product. It is helpful to read reviews and testimonials from other users to get an idea of the manufacturer's reputation. The cost of the UPS is an important consideration, but it should not be the only factor. It is important to balance the cost of the UPS with its performance, features, and reliability. A cheaper UPS may not provide the same level of protection as a more expensive model. It is also important to consider the total cost of ownership, which includes the cost of the UPS installation, maintenance, and battery replacements. Selecting the right UPS for nonlinear loads requires careful consideration of various factors, including THD, short circuit current capability, overload capacity, battery type, cooling system, communication capabilities, warranty, manufacturer reputation, and cost. By carefully evaluating these factors, users can ensure that they select a UPS that meets their specific needs and provides reliable power protection for their sensitive electronic equipment.